as
you ever try to do it?
I've tried it once.
It's hard because you can't rest your hand on the string, so you have to kind of be like this. Like, you know what I mean?
Yeah, I do. That would be really, really hard to write like that.
If you can just do this, then it would be fine.
Can I borrow the homework assignment from someone? Somebody print it out. Thank you. So apparently I'm a combinatorialist, but I can't count. So that's the right up-step set of this path P of the homework. Okay. Hopefully no one was confused by that. Okay. So I'll remind you where we are. The first day of class, I gave you a bunch of examples of what I said was going to be a matroid. And in the second class on Friday, I showed to you guys that basically, first I told you what a matroid is. And then I showed you why a collection of vectors gives you a matroid and why a graph gives you a matroid. And I left it as a homework exercise for you to show that a matching problem also gives a matroid. Okay. And let me just make two very easy technical definitions. Yeah? Sure. Yeah, sure.
Number 2.
Mm-hmm.
Can I just assume V is just Euclidean space, or do you want it to be a general vector space?
V is in problem number 2.
Yeah.
Let me see. V is an arbitrary vector space. It doesn't have to be Euclidean space.
Okay. And can you draw a dice hat?
Yeah. So maybe I'll draw and I'll tell you how to say it. So it's actually a dick path. And this dick path goes 1 step up, 2 up, 3 down, 4 up, 5 down, 6 up, 7 up, 8 down, 9 down, 10 down. This is 0, 0, and this is 10, 0. And this is the path that I called U, U, D, U, D, U, U, D, D, D. So up means you go up 45 degrees, and down means you go down 45 degrees. Okay.
Talking about the homework, based on what you've covered so far, should we be able to do all of those problems at this point?
Yes, since the class on Friday, you're ready to do all of the problems in the homework. So there's no additional theory that you're going to need to do them.
You do need the definition of bases for number 6.
Okay, so
that's it. Other than that, I think you've covered everything else.
That's true. So I guess that means that in the next 10 minutes from now, you will be ready to do any of these problems. Any other questions about the homework?
What was the third matroid? You said you gave us 2 examples.
And the third example is this example from a matching situation where you have some men and some women, and the men had their preferences of women that they were willing to marry, which is also, I think, question 5 in the homework. Okay. So let me just give you some names of things. So 2 matroids are isomorphic. Basically, they're the same thing. me say EI and E prime, I prime are isomorphic if they are the same matroid. And what that means is that, for example, in the 3 examples that I gave you, the first example, E consisted of vectors. In the second example, E consisted of edges. And in the third example, E consisted of women. But the matroid is the same. Okay. And this is all this definition means. And I'm afraid that I might actually scare you off by writing this, because really what I mean is the same matroid, the same list of independent sets, and the same ground set, except with different names. So all I need is a bijection from E to E prime, which induces a bijection on from I to I prime. But this sounds scarier than it is. All I mean is they're the same matroid. Same matroid with a different name for the elements. With different names for the elements of the ground set. Okay. That's what it means for matrices to be isomorphic, that they're the same matroid. Question?
About the ground set. Do you allow redundancy in the ground set? Like, can you allow the same element to be repeated twice? Like, for example, in a vector arrangement, can you allow the same vector to appear twice, but you consider it somewhat...
That's a good point, actually, and maybe you guys noticed that in the online forum, Andres from Colombia mentioned this, that he really wanted several vectors to be called 0 in order to solve problem number 2. You allow that. I mean, you allow, for example, in a list of vectors, maybe you can have repeated vectors. Okay?
So you just kind of label them differently, but they're the same in the range?
Yeah, exactly. Question?
The definition that you wrote there, like you do, so you need E and E prime to be bijective clearly before you could even start to talk about isomorphic matroids, but you do need to have, so that induces a bijection from I to I prime, but depending on your notions of independence on either side, you need to know a little bit more about that. That the definition of independence in E prime agrees with those subsets.
But remember that a matroid is just a set E and a collection of independent sets I. And you don't care where that collection comes from. So you forget that you're talking about linear independence. You forget what you're talking about. All a matroid is a set and a collection of subsets.
Okay, I think what I'm saying is, it seems the way that you've written it there, in my brain at least, to be, if I have 2 sets with the same number of elements, then their matroids are going to be the same. But that's not necessarily true. You can have different matroids on the same. If you label every set 1 up to n for some number of integers, you might be able to construct different matroids on those sets, right?
Right. So I mean, there's 2 things. So first of all, you need a bijection from E to E prime. So it's kind of a dictionary that says, okay, the element that you called A in set E, you called it A prime in set E prime. And then you have the second condition that this induces a bijection from I to I prime. What that means is that if set A, B, C is independent, then you look up that set in the dictionary, you find a set A prime, B prime, C prime, and I prime. That one is independent. And this is an if and only if. And these are the 2 elements that you need for an isomorphism. You need an isomorphism of the ground sets, a bijection, and then you need that to translate into, you have the same list. Same list of independent sets, except maybe with a different name. But again, the point that I want to make is that this is not a tricky definition. This is really exactly what you think two equal matroids are. It's just the same list of independent sets, except maybe you call them 1, 2, 3 instead of A, B, C. Okay? And then, so this is my first definition. And then I'm just going to define some words that you will hear all over the place. So a linear matroid is basically one that comes from a configuration of vectors. Okay?
So it'd be isomorphic to example 1 then?
To an example like example 1. A linear matroid is one isomorphic to the matroid of a vector configuration. Of any vector configuration over any vector space. Okay. Graphical matroid is one isomorphic to the matroid of a graph. Okay. And a transversal matroid is one isomorphic to the matroid of a matching problem. Okay. So what this means is that the matroid that I showed you the first day of class is a matroid that deserves to be called linear because we saw how it can arise from a vector configuration. It deserves to be called graphical because we saw a graph that realizes it. And it deserves to be called transversal because we also saw a matching problem where we got that matroid. Okay? And so these are three very important classes of matrices that we will come back to the whole semester. Okay? So in fact, maybe I'll even remind you what that matroid was because I'm going to need it in a second. So example, the matroid on the set A, B, C, D, E, F, whose independent sets are the empty set A, B, C, D, E. Then I think you had A, B, A, C, A, D, A, E, B, C, B, D, B, E, C, D, and C, E. And then you have A, B, C, A, B, D, A, B, E, A, C, D, and A, C, E. Okay. So this is a matroid, and we don't care where it comes from, and it just happens to be graphical, linear, graphical, and transversal. Linear, graphical, and transversal. Okay. Now let me make a definition, which is the last definition that you need for the homework, and that is a basis of a matrix. Is a maximal independent set. Maximal here means maximal by containment. Okay, so this means that you have a set which is independent, and no set containing it is independent. So maximal by containment. Okay. So for example, BD is not a basis because ABD contains it and it's independent. In this case, the bases are these 5 guys. In this example, my set of bases, which I'm going to call B script, consists of these 5 guys. ABC, ABD, ABE, ACD, and ACE. Question?
Yeah, in the reading that you posted online, talk about they kind of define bases through axioms. Can you talk about, well, the first axiom was the empty set is the basis.
Yeah, so let me, that shouldn't be an axiom, but
The empty set
yeah.
is not a basis.
But let me make a comment about that. So Vladi saw that in the notes. They define basis in a little bit of a different way. And in general, if you look in the literature, there's many different definitions of matroid. And I think next week, and maybe even the week after that, we're going to talk exclusively about this, how I define a matroid in terms of something called independent sets. Okay? But you could develop this theory from scratch by saying, no. I don't want you to think about independent sets. I want you to think about bases as the important thing. And you can say, a matroid is a set of bases that satisfy certain axioms. Or I know that you posted this question on the online forum that said, what about flats? So I read about something called flats. And there's another definition of matroids, which you see sometimes, that says, a matroid is a collection of flats that satisfies these axioms. Okay? This is one of the features about matroids that make them sometimes very useful and sometimes a little bit frustrating, that there are all these different points of view, and sometimes one is more useful than others. So what I'm going to say is, I'm going to start from the point of view of independent sets, and we'll slowly get to these other axiom systems that you've seen. But so far, I want you to think that a matroid is a ground set and a collection of independent sets. Question, Eric?
Just based on the examples we've seen so far, will it be usually the case that the power set for I will be too big? The power set for E being I.
Will be too big for?
For it to be I, the independent set of the matroid?
I is definitely a subset of the power set of E.
Sure.
And it could be the whole power set.
Okay, excellent.
So that's an example of a matroid, actually. Is E is a set, I is the power set.
Okay.
And it's an exercise to see that that is one of the many possible matroids that exist. Okay. Okay, what's the point of this definition? Well, the point is that it's kind of a waste of time to write this whole long list if you can just write this.
Yeah.
Why? Because what I'm going to show to you is that you can recover the whole list I if you have B. How can you do that? Basically, you say that the independent sets are the things contained in a basis. So, fact. The independent sets are the sets I such that I is contained in some basis. Why is that? Because look at an independent set. Then either it's maximal or it's not maximal. If it's maximal, then it's a basis. And that means it's contained in a basis. If it's not maximal, that means some other set, some other independent set contains it. And then either that one is maximal, or you can keep adding things onto it until you reach a basis.
Kind of from the second axiom, more or less?
From the
third, sorry. The third axiom. If you have a smaller set, you can always add something to it.
It's not even from that axiom. Like, in fact, let me say this explicitly. So you start with I. Okay? If I is a basis, you're done. If I is not a basis, then what happened? A basis is a maximal independent set. So if I is not a basis, that means that it is contained in a bigger independent set. It is contained in some independent set I. Okay? And then you say, okay, is J a basis? If it's a basis, then you just saw that I is contained in that basis. If it's not a basis, then because it is independent and not maximal, that means you can find another independent set containing it. So in fact, I'm not even using any of the independence actions here. All I'm using is the definition of basis. Okay. And you can just continue this process. How do you know that you're eventually going to reach a basis?
Well, everything's finite.
Because everything is finite. Because everything is finite, this process terminates. So here we go back to the discussion that I sent to the online forum. What if the matrix is infinite? We start to have issues. And I'd like you to discuss this. What happens to this argument in an infinite matrix? But I said that all the matrices that you're going to see in this class are finite unless otherwise specified. So because my matroid is finite, this process terminates. And I find a basis containing I. Okay?
So when you said start with I, you meant it's an independent set. I is an independent set already.
Start with I independent. Yeah, that's a very good point. Okay. So the point is that writing the set of bases is kind of a more economical way of writing the matrix. Writing B is more economical. Than writing I. So if I ever ask you to describe this matrix to me again, you're not going to go through this whole list, because all you have to do is tell me what the bases are, and I will know that the independent sets are the things inside the basis, the things contained in the basis. Okay? Any questions about that? Okay. So let me prove for you the first theorem about matroids. All the bases of a matroid have the same size. This is truly a theorem about matroids. It's not a theorem in linear algebra or in graph theory. It's a theorem about this axiom system of independent sets. Okay? Proof. Suppose not. Suppose that you have two bases of different sizes. Suppose that B1 and B2 are bases, and let's say that B1 is smaller than B2. Okay? And I see some of you nodding here, and hopefully you also see the advantage of matrix theory is that here you have these axioms, and all you can do is use axiom 1, axiom 2, or axiom 3. When do you have the situation? An independent set contained in another one. Almost the axioms themselves tell you what you need to do. We have this exchange axiom that says if this is independent and this one is bigger than this one, that means you can expand B1 with one of the elements of B2. So find an element B2 in the base B2 such that B1 union B2 is independent. And you can do this because of axiom 3. Actually, I don't want to call it I3. I think it's easier if I just call it the exchange axiom, and you remember that that's what it means. You exchange elements from one independent set to the other one. Exchange axiom. What did I just prove? I just proved that B1 was not a basis, because B1 is contained in an independent set that's bigger. B1 is contained in B1 union B2, and that means B1 is not a basis. Contradiction. Okay. So let's think about this. I just proved a theorem about matroids. And I also just showed to you three families of matroids that I can apply this theorem to. So let's see what linear algebra theorem I just proved, what graph theory theorem I just proved, and what transversal theorem I have proved. So for linear matroids, what does this say? For linear matrices, this shouldn't sound like a very exciting statement if I tell you something like this. All the bases have the same size. You know that. That's one of the things that you know in linear algebra, that vector spaces have bases, and bases are equicardinal. Okay? So this shouldn't be too much of a surprise. Not a big surprise, because of the notion of dimension. That is exactly the dimension of a vector space is the size of one of its bases. So for linear matrices, this isn't so exciting. What about for graphical matrix? Actually, let me just say a quick comment going back to linear matrix. Maybe this isn't a groundbreaking statement, but what I'm showing to you is that this statement and this notion of dimension really comes from this exchange axiom that happens to hold for linear algebra. Okay? This is very much along the lines of a point of view that many people are familiar with here. Probably several of you have taken courses from Sheldon Axler, where he has the point of view of he has this paper called "Down with Determinants," yeah? And his point is that linear algebra should not be about determinants if it doesn't have to be. Okay? And what I showed to you just now is that you don't need to be talking about invertible matrices or anything like this to make sense of this notion of dimension, which is really a matroid notion. And it's good to understand that. It's good to think about what linear algebra things are really linear algebra and which things are matroid theory. Okay? For graphical matroids, what is a basis of a graphical matroid? Let's think about that.
Well, it must be some kind of maximal subgraph with no cycle.
It is basically a maximal subgraph with no cycles. For now, let's assume that my graph is connected, and we'll talk about the case where it's not connected. And remember, connected means that you can walk from any vertex to any other vertex using edges of the graph. Okay? And let me define something called a spanning tree, which, if you have taken any courses in optimization in computer science, you have definitely seen this notion of spanning tree. A spanning tree is a subgraph which two things. It's connected and it has no cycles. Okay? So what you should be thinking of is this thing that really looks like a tree. You know, it doesn't go back on itself. You never form any cycles. And connected means that it's just a tree that touches every vertex. And so along the tree, you can walk from any vertex to any other vertex. That is what a spanning tree is. Okay? Hopefully this sounds to you like this should be a basis, and that's what we're going to show now, that a basis is exactly a spanning tree. So basis equal spanning trees. How do you prove something like this? In this kind of statement where you want to prove that two things are equal. This is a set of bases. This is a set of spanning trees. Usually you prove one inclusion and then the other inclusion. So first, let's show this inclusion, that every basis is a spanning tree.
That's clear though, right?
So what is a basis? A basis is a maximal independent set. So a basis is a maximal independent set. So it's independent, and that means you have no cycles.
How do we recognize it as maximal?
I don't know yet.
Yeah, that's
Or
the
in
other way.
general, when you talk in a definition of basis, it's a maximal independent set.
So whenever I say maximal, I mean maximal by containment. And so that means it's an independent set which is not contained in a bigger independent set. Okay? So what is a basis of a graph? It's a set of edges which forms no cycle, which is not contained in a bigger set of edges that form no cycles. Okay? So how am I going to prove that this guy is connected? Suppose it's not connected. So I'm proving that every basis is a spanning tree. So I need to prove that every basis is connected and has no cycles. I proved that a basis has no cycle. Now I'm going to prove to you that a basis is connected. So by contradiction, suppose that a basis is not connected. Suppose that my basis is not connected.
You assumed G was connected to start with.
So what means if B is not connected? That means that, let me just draw, imagine that this is the graph, and so there's some vertices and some edges. And let me draw the subgraph B, which is not connected. So it's something like this. It's not connected. It has several pieces. Okay? But we know that G is connected. And if G is connected, that means there must be a way of walking from this component to this component. Okay? I can walk from this component to this component.
Can we say that the components are also independent? If it's not,
We can say that each component is independent.
okay.
Why? Because if you had a cycle in a component, that's a cycle. If you have a cycle in one component, that's a cycle for the whole set.
Well, we already know the whole thing is that B is independent, right?
B is independent.
Yeah, B is independent to start with. We just want to show that it's actually maximal.
Right. And so what I'm saying is, let me call G is this big thing, and B is the blue subgraph. B is these little trees that I drew here. Okay. I know that in my graph G, I can walk from this component to this component. So I do it. I walk, and when I walk, it's pointless to walk on a cycle. Right? If I can walk with a cycle, I can walk without that cycle also. So I make sure that when I walk from here to here, I don't close any cycles because it would be silly to do that. And what did I just construct? I constructed a larger set which still has no cycles. And that cannot be because I assume that B is a basis. Okay?
So it's like a theorem for graph theory, you can go from different components with some path, no cycle.
It's not really a theorem. So several people have asked me about this. So what about this graph theory? I've never seen graph theory. There aren't deep graph theory theorems that you're going to need to use. You just are going to need to get used to these kinds of arguments. And I want you to think about it carefully, that what I'm saying makes sense. And if you've already seen a course in graph theory, then what I'm saying is maybe clear to you. If you haven't seen a graph theory course, then it probably sounds plausible, except you maybe want to think about it and make sure that what I say is correct. So please do that and think about it, but you'll see that there's no big theorem here. It's just the definitions of, it's just by definition. Okay. Suppose B is not connected, and then I constructed a set, an independent set, B prime containing B. B prime is this thing now with the red piece on there too. So that can't be. Okay. So that's one direction. Now let me show the other direction, that every spanning tree is a basis. So the opposite containment, that if you have a spanning tree, then that's a basis. So you take a spanning tree, T spanning tree. You need to show that it's a basis. And to show that it's a basis, you need to show that it is independent and that it is maximal as an independent set. So first thing, T is independent. Why? Because the definition of tree is that there's no cycles. So T is independent, that's obvious. And I need to show that T is maximal among the independents. Okay. So how do I do that? Well, kind of the backwards argument here. So I say, suppose T is not maximal independent. That means you have a bigger one. Then you have T inside some other set, let's call it U, where U is independent. So again, let me draw T, and T is some big tree that connects the whole graph. Okay? And now U, so this is, again, my schematic thing is that this blob is the graph, G. Here I have T, and U is supposed to be a set of edges containing T. So let's consider any other edge that is in U and is not in T. So let's say that, for example, I have an edge over here which is in U but not in T. This is in U but not in T. Can it look like this? No, because T already connected every vertex. Okay? So no matter what edge it is that I draw, I already had a blue path that went from this point to this point, because T connected everything. So from every vertex, I could go to any other vertex. By adding another edge, I'm adding a second path from this vertex to this vertex, and so what I do is I close the cycle. So any additional edge closes the cycle. And I don't want that. I said that U was supposed to be independent, and I just showed you that it's not independent.
So if you were to write that up without the picture, you would say, you have to have some extra edge in U that wasn't in T, so that edge must connect two vertices, but we already know that in T there is a path between those two, so that's the cycle.
That's right. So you just said exactly what you would write if I asked you to write a proof for this. Okay. Again, you might be unfamiliar with this kind of arguments, and I want to say two things about that. First of all, that the book on matroid theory has a lot of graph theory, and I think maybe you will notice that. And I want to point out to you guys that this course will not take that emphasis so much. So I'm talking about the graph example because it's a very important example. But this isn't really a graph theory course, and there's not really a lot of theory that you need to know. But I do need you to be comfortable with this kind of argument, and this is a matter of practice, and so you will get practice in the homework that I'm giving you, and if you don't see this proof right away, then make sure to think about it and that it's clear to you. Okay. But let's go back to what I was saying. I was talking about the theorem that all bases of a matroid have the same size, and I said that in a vector space, this shouldn't be too surprising to you. In a graph, what do you think? I mean, what I'm proving to you guys is that every spanning tree has the same size. Right. Is that clear?
Now that we've gone through that argument, is clear. It wouldn't have been clear 20 minutes ago.
Yeah, I mean, if I take someone that has never heard anything about graph theory and I tell them every spanning tree of a graph has the same size, the same number of edges, well, if you give them enough time, they'll be able to prove it, but I wouldn't say that's necessarily an obvious statement. But that is exactly what we just showed. We just showed that.
Well, we showed that bases have the same size, and spanning trees are bases, and bases are spanning trees. So.
I'm trying not to make a mess of my blackboard, so maybe I'll go back here. But exactly, so first we showed that bases have the same size, and then we showed that bases are spanning trees. So, of course, what did we just show? That spanning trees have the same size. So, proposition, the spanning trees of a connected graph have the same number of edges. How many edges? If you think about it a little bit, you'll realize that the number of edges is number of vertices minus 1. And I want you to think about that and make sure that you understand that. This is for a connected graph. What are the bases of a disconnected graph?
Unions of bases of its connected components.
Let's say the basis of a not necessarily connected graph. Not necessarily connected graph well, you know, so maybe here's my schematic picture of a graph, and maybe it's not connected. So what that means is that it has these little pieces here. So maybe this piece is connected, this piece is connected, this piece is connected, and this piece is connected. So these are these are the connected components. So what is a basis here? You can probably guess what it is you just put a basis on each one of these guys. Okay. So this part is connected, and so you just connect everything with a tree. This part is connected, and so you connect everything with a tree. So you just put a spanning tree on each connected component. If I force you to pick a name for this red thing that I just drew, what would you call it? Well, each one is a tree, so a bunch of trees is a forest. And this is what they're called. Spanning forests. Of the graph. So the bases of G are the spanning forests of G. What that means is a spanning tree in each connected component.
connected graph, the spanning forest is made up of a single tree.
Exactly. So a spanning tree is a special case of a spanning forest. It's a bare forest that only has one tree. If the graph is connected, there's only one piece. If it's disconnected, there's more pieces. And in fact, this proposition is still true if I remove connected. And instead of spanning trees, I have spanning forests. The spanning forests of a graph have the same number of edges. And what is the number of edges? You should think about it a little bit, and you'll convince yourself that the number of edges is the number of vertices minus the number of pieces, the number of components. Okay. And this is not so trivial. Okay. So there's my theorem for vector configurations and for graphs. Okay. Let's go to the third example for transversal matrices. What are the bases of a transversal matroid?
Everybody gets matched.
The bases of a transversal matroid are called transversals. That's where the word comes from. And let me just tell you two ways in which you can think of transversal matrix. So we saw one way, which is that you can draw a bipartite graph. It's the other way around. So I call these guys 1, 2, and 3. And these guys I called A, B, C, D, E, F. And so I had this. So this is one way of thinking about a transversal matroid is coming from a bipartite graph. Okay. An equivalent way is to instead of drawing the graph, what I'm going to do is just make the list of who each one of these guys is connected to. So I make a list. A1 is 1. A2 is 1. Sorry. A1 is A. A2 is A, B, and C. And A3 is A, B, C, D, E. And what is a transversal of something like this? A1 up to AN.
So you have to go
a set of n elements. What you want to do is pick a y for A1, pick a y for A2, pick a y for A3, and have them be different from each other. Okay?
What if you can't?
Maybe you can't. Okay.
'Cause you
But
could
then there's no transversals.
Huh? Oh, there might. Okay.
I mean,
so
it might be that no one wants to marry anyone, and in that case, there's no transversals.
No, I mean, but say what if, for example, you could set up the problem so that A1 and A2 both only want an A, and they're going to fight to the death over that one. and then A3 is still how he is up there. So you could never satisfy both A1 and A2. So in a sense, they're kind of the same one, but they're not necessarily.
That's a very good point, and it actually is very related to the difference between a connected graph and a disconnected graph.
Okay.
So there's kind of a transversal problem where everybody can be happy, and then there's problems where not everybody can be happy, and then it's a little bit different. And there's a similar situation in vectors. Okay, so maybe the vectors span the whole space, or maybe they don't. Okay.
Oh yeah, exactly.
So
exactly, yeah.
we'll see more about that, but let me assume that I have a situation like this one, where a full matching is possible. So a transversal is a set of n elements which I can label A1 up to AN, so that A1 is in my first set, and so on, until AN is in my n set. Okay. Now, that's why I said a set of n elements. So if I say that, I'm implying that they're distinct. Okay. So this is what a transversal is, and these are the basis of these matroids. And what you are going to prove in the homework is that this is a matroid. Now, what is this statement saying about transversals?
With the statement about everything being the same size, bases.
Right. So what is the statement that bases have the same size saying here?
It's basically saying that the same number of people get matched.
It's saying that every maximal matching has the same number of couples. So what that means is, if you manage to find a full matching, then any partial set of people that you could marry can be expanded to a full set of people that you could marry. So you might call it a partial transversal. Can be extended to a full transversal. And this again is not obvious. I think this is even less obvious than the previous two statements.
Assuming that such a transversal exists, a full matching.
Yeah, notice that I'm not saying that every partial matching can be extended to a full matching. I'm saying every partial transversal can be extended to a full transversal.
Oh, full transversal meaning the biggest transversal that you can
Right.
have. Okay.
Because, for example, here is a partial matching, 2 and A, 3 and D. There's a partial matching that you cannot complete.
Yeah.
Because you can't marry one to anyone. But the transversal AD can be completed. You just have to remarry these guys and then marry A, B, and D. It's different. So that's what this means. Every partial transversal, like A and D, can be extended to a full transversal. You might need to remarry people, but you can do it.
Tell me again what a full transversal is in regard to the matching of these people.
A full transversal is basically a set of women that could be married. So, for example, A, B, and D is a transversal. And the reason is that you could marry 1 to A, you could marry 2 to B, and you could marry 3 to D.